Hello everyone, today I'm going to talk about a problem in guided waves, which is a topic of classical electromagnetism. Now the tagline of the problem is TEM waves, which is a full form for transverse electromagnetic waves, guided by a conducting cone and a conducting plane. We'll actually analyze different kinds of possible solutions guided inside the cone. Let me draw the scenario. Assume the plane is the z equals to 0 plane, and upon it there's a cone which apex is on the z equals to 0 plane. And I want to investigate what kind of transverse electromagnetic waves are supported by this scenario. Now, let me read the problem statement from the book. It tells to consider time-harmonic solutions to the Maxwell equations in vacuum. So obviously the charge density and the current density will be 0. And the fields will be independent of the azimuthal angle, which is commonly denoted as phi. The azimuthal angle is one of the angles in spherical coordinate system. And we are also assuming that the radial components of these fields are 0. Now, let me remind you that both of this plane and this cone are actually perfectly conducting. That means that the electric component, the tangential electric component on this cone and on this conductor will be obviously 0. And I'm gonna denote the tangential component by this will be 0, and the normal component of the magnetic fields will also be 0 in the cone, at the surface of the cone and at the conducting surface z equals to 0. Now the problem tells you to consider about only time harmonic solutions of the Maxwell equations. So the electric and magnetic field will be obviously of this type. And remember, there's no phi dependence, so I'm going to write it like this. And this exponential term is the time harmonic part of the solution. Now, the magnetic field will be of similar kind. This will also be independent of the azimuthal angle, so no phi dependence here. And there will be the time dependence, which is a time harmonic function of this exponential type. Now, for time harmonic electric and magnetic fields, the Maxwell equations, which denote the curl of a electric field, which is like this. As you can see, there is an exponential dependence of time here. What we're gonna have is that the amplitude term will be just here, and we will have the derivative term over here. Okay, so this would be just I omega b r theta to the power minus a omega t. Now, the last part is just the magnetic field. This is just the magnetic field. By a similar calculation, you can get from the Ampere-Maxwell equation, which is this in general, but as it's a vacuum, there will be no current density. It is like this. Using the same kind of mathematics that we used here, we can show that it will be just minus I omega c squared e r theta. This will be time actually. Now let's look into the components of these two equations that we have got here, which are correspondingly this and this. Okay, as you can see, the problem states that there is no phi dependence and the components of radio components of electromagnetic fields are zero. So obviously the suitable coordinate system is spherical coordinate system. And in spherical coordinate system, we have the expression for curl as this. This is the radio component, and the theta component is this. This is phi actually. Let me rewrite it. And the phi component, let me write it, is this. Now this is for the general electric field, but we have already assumed some conditions here that the radio component will be zero and there's no phi dependence. So we can actually simplify this big expression by writing this. So here you see there's a phi derivative, but we have already assumed there's no phi dependence, so only the first term will stay here. And there is also a phi derivative here, which will be zero. And I'm going to write this second term. This would be just, there will be a minus in front of it, dre phi dr theta. Plus, as you can see, we have already assumed the radio component is zero, so the first term will remain here. So it will be 1 over r dr e theta dr phi. Okay, we will get a similar expression for curl of B, right? Because we have assumed the similar type of assumptions in case of magnetic field too. Now, as you can see from the Faraday's law and the Ampere's-Boltzmann law, we can work out the different components on both sides. So what will happen is we will now think about components of the Faraday equation and the Ampere-Boltzmann equation. Ampere-Maxwell equation. So let's start with curl of E. So the radial component of the curl of E is this, but we have the magnetic field here, and the radial component of magnetic field is zero. So This term here will be 0. So let me write it here. 1 over r sine theta over del sine theta e phi d theta will be 0. And similarly, the radial component of the magnetic field's curl will also be 0. So we have a similar type of equation. As we have assumed similar type of assumptions in magnetic and in case of electric field, this equation will be similar. And now let's look at the theta and phi components of curl of E and curl of P. So the theta component of curl of E, and let's look at the Faraday equation here. So it would be I omega B theta here. I omega B theta. Similarly, we will have 1 over r dr d phi dr I omega E theta. Now, about the phi component, it will be like this. I omega beta phi omega, and in case of the magnetic field, it would be like r e d theta, and okay, this would be, let's see what's the ampere Maxwell equation. So there's an I minus I omega c squared, and there will be the phi component of electric field. Oh, sorry, this would be also minus I omega c squared. Now we have two sets of equation, one for the electric fields in this side and for the magnetic fields on this side. Now in part A of this problem, the book tells us to find two different sets of solutions which are very different from each other. Actually, they are linearly independent. Here's how you can find these two linearly independent solutions. Suppose E phi is 0, so only E theta term stays, because if you want to have a wave, one of the components has to be non-zero. Then you have this B phi term associated with it. Now, you can think in the other way too, where E theta is 0 and E phi is non-zero. Then we have a corresponding B theta component here. So what you see, you get two independent solutions, linearly independent solutions. One is E theta B phi, and the one is E phi B theta. In part B of the problem, the book tells us to start from the divergence equations from the Maxwell equation and find the solutions to TEM waves in this particular situation. Now you know that in vacuum charge density is 0, so this right side is 0 here. Now let's look into what's the expression for divergence in spherical polar coordinates. So this is like this. Plus 1 over r sine theta del sine theta e theta del theta plus r sine theta del e theta del phi. Sorry, it would be phi here. Now there's no phi dependence, so this term is 0. Er is 0, so this first term is also 0. So we are left with this second term. Which is 0 by this equation. Now, in case of the magnetic field, we will have a similar equation. Now, if you go back into the video, into the part A, you'll find that we have some similar equations from the Faraday and Ampere Maxwell's law, which are for the E phi, and I'm gonna write the equation for B phi here. Actually, I'm grouping these two equations because together they actually work for the E theta B phi solution, and these two actually work for the E phi E theta solution. Now for case E theta B phi, which is one of the independent solutions in this scenario, I can solve the E theta equation by direct integration. So as you can see, this part is actually not 0, so we can multiply both sides by it. And as you can see, the partial derivative with respect to theta here is 0, and E theta is actually a function of r and theta because there is no phi dependence. We can write it as a function of r, which is actually called E tilde theta r. Now we can just simplify it to get this. And as B phi also satisfies a similar type of equation, B phi will also have a similar solution. Now for the E phi B theta solution, we will have similar type of functions for E phi and B theta because they satisfy a similar type of equation. However, these four equations that we have here, this and this, this, are still not the solutions because these terms are actually unknown. So now we will use the rest of the Maxwell equations, which we have dealt in part A, to actually calculate this unknown stuffs that we have here. If you go back into the part A, where I have shown from the Maxwell and Ampere's law and the Faraday's law that these two equations are satisfied by E theta and P phi. So we have already seen the form of E theta, which is something like this: E tilde sine theta equals to I omega B theta, sorry, phi r sine theta. Now I will just cancel the sine theta from both sides and I will get this. Now if I take another derivative with respect to the radial coordinate, I get this. Now in the right side I have this radial derivative term, which I will calculate using this equation that we have here. So let's divide this to part. If I write the form for B phi and E theta here again, I'm just gonna get R B tilde phi and I omega C square R E theta. Now I'm going to use this equation into the equation that we have just got here. So you will see it will be just omega over C squared over R B phi over R. Now this equation resembles the simple harmonic motion differential equation, which has a very simple solution. The solution will be R E theta R equals to some arbitrary constant. Let's say it's ER. Another arbitrary constant. Now using this here, I will get the E phi form here. So as you can see, I would just have to integrate this function with respect to R to get this B phi expression, which will be something like, as I'm integrating, let's write the terms in front of it first. It would be ER EI omega RC ER EI C times minus I C omega. So what we have got here, let me write it here. So now E theta R theta, as we have seen before, is just E tilde theta R divided by R, sorry, sine theta, which will be just this R sine theta ER e to the power I omega over I omega R over C plus e to the E prime to the power minus I omega R divided by C. Now for the B phi, we'll get a similar type of situation here. As you can see, I will cancel the omega and C will cancel out, and I times minus I equals to 1. So 1 over C ER e to the power I omega R C minus ER to the power minus I omega R divided by C. So similar equations that we have here divided by sine theta. So it would be 1 over C R sine theta E R omega RC minus ER over C. Now for the E phi E theta solutions, we will have similar type of solution because they also satisfy similar type of differential equation. So well, I'm not going to solve that part because it's similar. In part C, the book tells us to show that only one type of solution that we have found here is actually a possible solution in the scenario we have here, where a cone is situated above the z equals to 0 plane, and the wave is inside this cone, right? Remember, whenever we have some guiding medium like a coaxial tube or anything which is made of perfectly conducting walls, we have this boundary condition which says that the tangential component in the surface of the perfect conductor, the electric field, actually the tangential component of the electric field will be 0, and the normal component of the magnetic field will be 0. Now, let me draw the unit vectors in spherical polar coordinates. Let's suppose this is the cone here, and this would be actually the theta hat unit vector, and along this direction will be the phi hat vector unit vector. And if you have E phi solution like this, so as you can see, this phi hat is actually tangential to the surface of the metallic cone. So if you have a non-zero E phi part, so this condition here is not actually satisfied. So this type of solution is actually not possible in this scenario. So the only possible solution is actually this, and all the solutions that you can find for transverse electromagnetic waves will be actually of this type, right? So this was the solution of the problem. I hope you enjoyed it. If you liked the video, please hit the like button, subscribe to my channel, and let me know in the comments what kind of problems would you like me to solve in this channel, because I want to talk about the motivation for different problem solving techniques in physics. Until next video, goodbye.